All right, so before we start our 8.2 notes, what we're going to go over is some rules for exponential graphs. Usually this would have been a warm-up, so you would have had it also in your notes from your 8.1 stuff. But since obviously we're not in school, then we will do it on here with our 8.2 notes. So some rules for your exponential graphs. This would be a general case scenario for an exponential function. And there is a way for you to identify what the domain, the range, and the asymptotes are going to be just by looking at the graphs. Now there's two different scenarios though, and that all depends on the A value of the graph. So if the A value is positive versus if the A value is negative, there are your alternate rules. So either way, if you're looking at your 8.1 assignment, you should notice that every single one of your domains is always going to be all real numbers, whether your A value is positive or negative. So that rule doesn't have an effect on it. Your range, though. Your range was always either a number to infinity or from negative infinity to a number. And you should notice that number was always affected by the K value because that was your vertical shift. So if you have a positive A value, then your range is going to be from that K value. Remember, it's never going to touch that K value. It's going to be approaching it. So from that K value to infinity, or you'd be able to write it as f of x is greater than. Not greater than or equal to, just strictly greater than. And then it would be the opposite if your A value was negative. So you would have f of x goes from negative infinity up to k, or f of x is strictly less than k. So that's the big one that changes with your A value. Now your asymptote is always just going to be that horizontal line, and that actually happens at k also. So whether it is positive or negative, that just tells you whether the graph is going to be above or below that asymptote, but that asymptote is still going to be y equals k. So those are some general rules. So you should always be able to figure out your domain, range, and asymptote just by looking at your function. All right, so now that we know those basic rules about exponential functions, let's actually talk about solving exponential equations. So our goal today will be to solve exponential equations. All right. So the property we already talked about, that b cannot be 1 because then of course it is not an exponential equation. So that part of this property of equality for exponential functions shouldn't be any different. And we talked about b is not negative, so that's where it says b is greater than 0 in an exponential equation, because what they're talking about is b is that growth factor. So that's the base, and then the variable is the exponent. But in this case, what we're talking about for the property of equality is if I have the same base, okay, you have b taken to a power of x is equal to the same base but taken to a different exponent, then those exponents have to still be the same. So that's what it says, if and only if x is equal to y. All right, so that's the big thing for today, is that property of equality, because that will help us with solving these equations. So for our first problem, you notice that both of those sides, the left and the right, both have a base of 3. So that means that the exponents have to be equal to each other. So that 4 and the y are going to be set equal to each other. So 4 equals y. There's your answer. Y is 4, and you're done. For the next one, in number 2, again, these ones also have the same base. So since they both have a base of 5, you then have to set the exponents equal to each other. So those exponents are 2x and 10. So you know 2x has to equal 10. So this one has a little bit more work to it because you have to actually go about solving for x. But that's just simple stuff that you guys have been doing since junior high when it comes to solving that linear equation. So x is 5, and you're done with that one as well. The next one might look a little bit trickier because the bases are both x, but since the bases are the exact same variable, it is no different than if each of the bases were 3 or 5, like in numbers 1 and 2. The base is a variable, but it's the same variable, so the same idea here. You're just going to set 2 is equal to 3y, and then you'll be able to solve for y. Y will be 2/3, and you're done with that one also. All right, so number 4 is where it gets tricky, because the first thing you should notice is 2 and 8 are not the same base. So this is where your powers chart comes in handy. So if you remember that powers chart that we handed back during Unit 7, that's a good thing to have out because it will help you come up with the same base. So you're looking for a base where there is an exponent that the answer would be both 2 and 8. And in this case, that base would be 2. So you want to write these both with the same base. So 2 is already written that way, so you have 2 to the power of x. Now 8 is the same thing as 2 to the third, so that's where that powers chart comes in handy, because if you're looking at the base of 2, you'll see that if your base is 2, you can get answers of 2 and of 8. And then that shows you a different way you can write 8 but not change the quantity of it. So 2 to the third power is still 8, so you just rewrote how it was written. So now that we have the base of 2 on both sides, this one is being raised to the power of x. Now this brings back our exponent properties. So when you take powers to powers, 3 to the 4th power there, 2 to the 3rd to the 4th power, you're actually multiplying those. So this is 2 to the 12th power. And now you have the same base, and you can set those exponents equal to each other. So x will be 12. All right, so same idea with number 5. You have to figure out what would be a base that you could write to a power that you could get the answer of 3 and 27. If you use that powers chart, or if you, this one you might know in your head, that you can write 3 to the 1st power, and 27 is 3 to the 3rd power, so that base would be 3. We're not changing anything else yet. So this is then 3 to the 4th power, because again, you're multiplying. When you're taking a power to a power, you multiply those exponents. And over here, 3 times x is just 3x. So now we have the same base, and so you're able to set the exponents equal to each other. 4 is equal to 3x, and solve from there. And you should get x is 4/3. All right, so this next one, you'll notice that there's, if you're looking at your powers chart, you might be a little confused because you're like, well, there are 4 and 64 in 2 different columns. And so I'm going to show you both ways that you can go about this problem. So writing 4 and 64 with the same base, probably most of you will use this first method to do this. 64 is the same thing as 4 to the 3rd power. So you could do it this way. The other option is you could write them both with a base of 2. So I'll show you that one in a minute. But here we have 4 to the power of 2n minus 1 and 4 to the power of 3. So you are going to set 2n minus 1 equal to 3 and then solve from there. And you're done. Okay. The other option here is if you did use the base of 2. 2 squared is 4, so that's how you'd write the left side. You haven't done anything to the exponent or anything. 64 is 2 to the 6th power. Okay. But the thing here on the left side that you want to be careful is if you're taking 2 to the power of 2n minus 1, remember you are multiplying, but you have to multiply it by this whole expression. So you actually have 2 to the power of 4n minus 2, because 2 times 2n minus 1, you have to remember you're going to distribute that 2 to both terms there. So that's the left. The right is still 2 to the 6th power. Now that you have the same base of 2, you can go ahead and set 4n minus 2 equal to 6 and solve. And either way, you're going to get n is 2. All right, so we'll keep going. This next one, you're looking for a common base between 5 and 125. So if you look at your powers chart, that common base should be 5. And it should be 5 cubed is 125. So this one's 5 to the power of 5x. And on the right side, again, you're going to have to multiply 3 by x plus 2. But just like in number 4, that second option I showed you, that 3 has to multiply by both x and the 2. So you're going to have 5 to the power of 3x plus 6. Then you're going to take your exponents, set those equal to each other. And solve. And we should get x is 3. All right, so number 8, you're going to look for how can you write 9 and 27 with the same base. So if you look at your powers chart, that common base should be 3. So 9 is 3 squared, so you're going to write 9 is 3 squared, still raised to the power of 2x. 27 is 3 to the 3rd power, still raised to the 3rd power. So the left side would be, again, you're multiplying those. So you'd have 3 raised to the power of 4x is equal to 3 to the power of, 3 times 3 is 9. Now you have a common base, so you can set 4x equal to 9 and solve there. And you'll get that x is 9/4. All right, so this is a technique actually that we do not only do in 8.2, but we will be using this same technique in multiple other sections. So it is really important that you get the hang of this, which is why we did so many of those examples. Couple different story problems in this section, one of them being compound interest. So this is super important because this is banking. Any savings account is compounded usually monthly. People will receive a statement every month, and typically you'll earn interest in that. And so the way that it is calculated to the interest that you are is using this formula, this compound interest formula. Now notice in the different variables that we're using, you want to make sure that the units are consistent. So I'm bringing this up because we're going to get into this with you guys writing your own formulas eventually. So your amount that you're actually finding is after a certain number of years, where your principal amount is in dollars. The R value is going to be your annual interest rate. So annual years, those all match up. And you are going to write it. It's going to be given to you as a percentage, but you're going to have to be able to transfer that into a decimal. N is going to be the number of times that's compounded within a year. Most accounts are, like I said, compounded monthly, but depending on what story problem you were given here, it will tell you. So like in number 2, it says semi-annually is when it's compounded. Number 1, it's compounded monthly. So you'll have to figure out the number of times it compounds within that year. And then T is representing the time in years. All right, so let's tackle this first problem. What I like to do is I actually write out all of my information first. So all the variables A, P, R, N, and T. And then I write what each of them are, and then you know also which one you're doing. So you're trying to find the balance of an account after a certain amount of time. So The big question is A. That's the one you're not going to know. That means in this problem, you are given all 4 of the other variables. You just have to be able to match it up. So P is your principal amount. That principal amount is the initial amount, the amount that's started in the account. So in this case, it is $451. Your interest rate is 3.2%. So then in order to write that as a decimal, it's going to be 0.0325. Remember, percent means to divide by 100. And the number of times compounded annually. This says it compounds every month, and there are 12 months in a year. So N is going to be 12, and then T is the time in years. So if you're reading it, you want to find the balance of the account after 10 years. So your time is 10. So now you have everything except for A, so you're going to fill it into our equation. Okay, so that's part usually my students tend to understand. It's when they go to put it into their calculator is where things get lost. A lot of times that they'll take it to the 12th power, and once they find that answer, they'll then multiply by the 10 because they'll forget to put parentheses around the 12 and the 10 here. To prevent that, what I usually do is I will usually just replace this and actually multiply 12 and 10 together and change it to the 120. So go ahead and punch that into your calculator, and I want you guys to do that right now while we're doing this to make sure that you're getting the same answer as I am. And then if you did punch that in correctly, you should get $623.92. Whenever we're dealing with money, you always want to make sure to round to the hundredths place because that's how we talk about money, to the nearest cent. So make sure you do that. All right, so into the next one. All right, so find the balance of the account. So we're trying to find the balance. Again, we don't know A. And it says after 18 years, so there's your time. If $25,000, there's your principal amount, is deposited into an account paying 2.3%, so we need to write that 0.023. N is the number of times it's compounded, and this one's done semi-annually, so twice a year, so 2. We're going to plug this all in. I'm going to figure out 2 times 18, so I don't have to worry about putting that into the calculator wrong. And once I put that into the calculator, my final amount should be, again, remember to round to the nearest cent, it's $37,732.18. All right, this last problem is a story problem, but it is representing, there's actually quite a few problems on the assignment that goes along with it that says to write an exponential function for the graph that passes through the given points, and it's going to give you 2 points. You'll notice always the first point is 0, a number, and the second point could be anything. But what you're going to do is you're going to write the function for a graph that passes through the 2 points. There's also a story problem on your assignment, so I did this example as a story problem, so you guys can see that that's where where that assignment's going. And apparently I forgot to edit this because I did not give you the first problem with just the 2 points. So there initially are 2 rabbits. Okay, so the initially, remember how I said that first point's always 0 comma something? 0 comma, so initially is at times 0, and there are 2 rabbits here. And the population is growing exponentially, which tells you that you're going to be writing an exponential function. And then it says for after 4 years, there are 162 rabbits. So the next point is going to be 4 comma 162. Okay, so it gives you the 2 points. All right, so then once you have those 2 points, now we can work at actually writing the function. So remember our function, the way that it is written, it's in the form of y equals a times b to the power of x. X is going to be your time. Okay. Your b is your growth factor, or your growth rate. Okay. A is always the initial amount. All right. So we already know the initial amount here. That initial amount was 2. So we can already start by writing y equals 2 times, the part we don't know is b to the power of x. So in order for this to be an equation always has the x and the y, but you need to figure out what that b value is. Now, we already did our work with that 0, 2. Right? That was our initial rate. So now that we have the second point, 4 comma 162, 4 is the x, 162 is the y. So we're going to figure out if we can plug that in order to calculate what the b value is going to be. So our y value is 162. We don't know the b. And the x was 4. Okay, so we have to get b by itself in order to solve for it. So the first thing that we're going to do is divide by 2 on both sides. That leaves 81 as b to the 4th power. Now, you might remember, but we've done this before, where we have to solve to the 4th power. So something to the 4th power. So you can either do it 2 different ways. You could take the 4th root of both sides, or you can take both sides to the 1/4 power. I prefer to do it that way. It does not matter if you take the 4th root or take it to the 1/4 power, but that was something we discussed in Unit 7. The reason why taking it to the 1/4 power, powers to powers multiply, 4 times the 4th is 1. So on the right side, you're left with b to the 1st. Now when you type it, you can do the left side into your calculator. So 81 to the 1/4 power, when you put that in your calculator, you should get 3. So b is 3. That's not the answer, though, because the answer tells you have to write this as an exponential equation or an exponential function. Okay, so our equation or our function is f of x or y equals, it doesn't matter, is our initial amount was a, so 2 times the b value we found was 3, so 3 to the power of x. That is your equation. Okay. Now, in part B, it says, if the pattern continues, how many rabbits would there be in 7 years? So it wants you to figure out, okay, so 7 years is your new x. All right, and then you're going to plug that into your function that you wrote. And now use your calculator, because I don't think many of you want to figure out 3 to the 7th power in your head unless you're using your powers chart. So you're going to have 4,374 rabbits. And that would be your answer. So there are your 8.2 notes. And now you guys can hopefully do the assignment.